As you see in this lecture, we're going to discuss the definite integral. Now, it probably has gotten past you. I've used the terminology before when we said integrate. I've used the terminology before, find the indefinite integral. So up to now, that's what we've been doing. You know, the indefinite integral will compare. That's kind of the important thing that we need to know here. The indefinite integral is what we're used to. That's the antiderivative, or an indefinite integral, pardon me. Okay, it's what we're used to. For instance, we see an integration sign, and maybe we have the integral of x squared minus 3x plus 1 with respect to x. And when we integrate that, we get what? 1/3 times x cubed. And then we have minus 3 over 2 times x squared plus x plus our constant of integration. So this is called an indefinite integral, and that's what we've been doing. Now, we're going to do something called find the definite integral. And we're not going to do this in this particular case, but a definite integral looks very similar. Okay, a definite integral might look like this. It might look like an integral sign, but besides just the integral sign, we'll see a little number down here, like maybe a 2, and a number up here, like maybe a 4, and then everything else will look the same. Okay, everything else would be similar then. Well, when we see the numbers on the integral sign, that's called a definite integral. And the definition of a definite integral has to do with a limit. It's a very complicated definition. But suffice it to say for us, what we need to recognize is when we talk about an indefinite integral, our answer is actually a function, isn't it? When we talk about a definite integral, our answer is a number. We'll actually get a number and not a function. And that number could be a negative number, it could be a positive number, or it could be 0. It could be negative, positive, or 0. It might be a fraction, it might be a whole number. Those are the kinds of things that we have to understand what we get. Now, let me tell you what the definition is, okay? So the idea, and so in general, let's do it this way. We'll look at a lot of examples, so don't panic yet. For a definite integral, in general, we'll have an integration sign with an A and a B. And normally, the number on bottom is the smaller, and the number on top is the larger. And we call those the limits of integration. Okay, so this is the lower limit of integration. And the number on top, which is normally larger, is the upper limit of integration. Now, we will be integrating a function, so I'm just referring to that as f of x, lowercase f of x. And this is the result we get, or the way we calculate the result. The result will be a capital F of x, and then we might see a symbol like this with that same A and that same B in this orientation. And what this means for us to do is to take the number B and put it into the function capital F. And then we subtract what we get when we take the lower number and put it into the function capital F. So remember, capital F is a function, and when we do f of b, we'll get a number, and when we do f of a, we'll get a number, and when we subtract those two numbers, that is the value of the definite integral. Now, there's something special about this capital F. This capital F is an antiderivative. okay? And this capital F is actually the indefinite integral of the lowercase f that we were looking for. That's what capital F is. You know, remember what that means. Remember that capital F being an antiderivative, if we take the derivative of capital F, we get lowercase f. But the real thing to remember is the way we calculate this capital F function is we first find an indefinite integral. And then when we find that indefinite integral, that's the function that we use to calculate the number. Well, I think an example will go a long way. And of course, well, like I said, we'll look at several different examples. It'll go a long way into telling us how we're going to proceed here. So let's go to the next page to look at the first example. Okay, you see the first problem here, the first example, and it says evaluate, here's the way we read this, evaluate the integral from 0 to 2. See, from the lower number 0 to the larger number 2. So integrate from 0 to 2, 8x cubed with respect to x. So we really do this in a couple of steps. And the very first step that we need to use is that we're looking for that capital F of x. And remember what we do to do that is we look at the indefinite integral of 8x cubed with respect to x. So this is just what we're used to doing. So the way we integrate, of course, 8x cubed is we say, okay, here's our 8. It's going to hang around. And to integrate x cubed, we increase the power by 1. And then we have to offset that new power with the reciprocal of the new power, which is 4. The new power is 4, and so the reciprocal is 1/4. And then don't forget our plus our constant integration. And so here we get the result. 8 times 1/4 is 2, so we get 2x to the 4th plus c. Okay, now here's the way the definite integral goes, now that we know that. The definite integral from 0 to 2 of 8x cubed with respect to x is this function. I'm going to put it in big brackets here. It's this function 2x to the 4th plus c evaluated from 0 to 2. Now what that means is we put the top number in for x first. So that top number, that 2, goes in for x first. So remember what we're doing. This is kind of a reminder. We're evaluating f of 2 and subtracting f of 1. And remember that is capital F. Remember, capital F is 2x plus 4, 2x to the 4th power plus c. So when we put 2 in for capital F, we just replace this x with a 2, don't we? So we'll have, let's write it in here, we'll have 2 times, instead of x, we have 2, and that's to the 4th power, and then plus our c. And then we subtract what we get when we put, oh, what did I do here? That's f of 0 over here, I apologize. Okay, then we subtract what we get when we replace x with 0. So when we replace x with 0, we have 2 times 0 to the 4th power plus a c. And then we just do the arithmetic or the algebra that's involved here. Now, again, let me point out, this is the capital F of 2 part, and this is the capital F of 0 part. Okay, now we're just going to simplify this. So we recognize that 2 to the 4th is 16. So in these first parentheses, we have 2 times 16, or 32, plus that constant. Minus over here, well, 2 times, of course, 0 is 0 to the 4th is 0, and 2 times 0 is just 0. So we have 0 plus c, or we just have c in this position. And then we notice that what this gives us is a 32 plus c subtract c, which is just 32. Okay, so the answer, remember as we said, a definite integral has an answer that's a number, and in this case it's a positive number, but this is the answer to our problem. This is the definite integral that we were just talking about. Now, I want to point something out because I'm going to change the way I do this a little bit in the future. Notice this C, let's kind of follow this C along. Here's that C, and now that C appeared in this part, and it also appeared here. And anytime we have an indefinite integral, we'll have this C, won't we? And when we have this C, it will appear in the first part because it's part of the indefinite integral. So it'll apply in the first part that we have here, and we're subtracting, and it'll appear in the second part that we have there. So we're always going to end up with a C subtract C. So if we're always going to end up with a C subtract C, why don't we just assume that, and in the future we won't write this constant of integration in when we're doing definite integrals. Not when we're doing indefinite integrals, but when we're doing definite integrals, we'll ignore the constant of integration, and it will just make things easier for us. We won't have to deal with the C everywhere, and we'll still get the same result. We'll still get 32. Okay, well, let's look at another example. We'll gain some momentum as we're moving along. Okay, as you can see, example 2, we're to integrate from -1 to 0, x minus 4 with respect to x. So just kind of keep in mind what we need to do. I'm not going to write down capital F of x, but what we need to do, and it's going to be this way all of the time, is we first need to find the indefinite integral. So we're looking for the indefinite integral of x minus 4 with respect to x. Well, the indefinite integral of x, we increase the power by 2, and we offset the new power with the reciprocal. So we get 1/2 x squared, and then we have a minus sign. And the integral of just 4 is 4x. Okay, now normally, so we have minus 4x. Now normally we would add plus a constant of integration. But since our ultimate goal is to get this definite integral, we know that constant's going to subtract out, so we're not going to put a plus c at this time. Now, we'll use this result to calculate the definite integral. And so remember that the definite integral from -1 to 0 of x minus 4 with respect to x is the indefinite integral, capital F of x, evaluated from -1 to 0. I'm going overboard here, and I'm just reminding you that that capital F of x is what we got on the first step. That's the indefinite integral without the constant of integration. Okay, so that tells us normally what we would do is we would make sure that we understand what our capital F of x is. So I'm putting it in parentheses, and we evaluate that from -1 to 0. Now we read it from -1 to 0, but to do the evaluation, we put the top number in first. So we're writing in the top, we're replacing x's with the value 0 in our expression. So we'll have, instead of 1/2 x squared, we'll have 1/2 times 0 squared. Minus, instead of 4x, 4 times 0. So that's what we get when we put the 0 value in, and then a subtraction sign. And we're going to now evaluate this function when x is -1. So that means we'll have a 1/2, instead of an x squared, we have a -1 squared. And minus 4 times x, but instead of x, our x is -1. See, these represent x values. That's what those are. Maybe I didn't make that real clear before, but they're the x values that we use. So now it's a matter of doing some evaluation. And in this first set of parentheses, we note that 0 squared is 0, 1/2 times 0 is 0, and 4 times 0 is 0, so we have nothing more than 0 subtract 0, don't we? So in these first parentheses, it simplifies to 0. Now in the second set of parentheses, we have a -1 we're squaring, and when we square -1, we get +1. And so 1/2 times +1 is 1/2. And then in the second part, we have a negative 4 times a negative 1. That becomes positive 4. And so we end up with something that looks like 0. Well, can we not add 1/2 and 4 together? I mean, now it's a matter of arithmetic. Okay? What we end up with is 0, and inside these parentheses, 1/2 plus 4. Well, let's go over here to the side. If we're going to have to add 1/2 plus 4, we need a common denominator. And so we'll write 4 as 8 over 2. So this is 1/2 plus 8 over 2, isn't it? That's what 4 is, 8 over 2. And of course, now we can see that that's 9 over 2. So in the parentheses, we add together and we get 9 over 2. So it's simply 0 minus 9 over 2, which of course is just negative 9 over 2. And that's the way we'll leave our answer. We don't need to write it as a mixed number. We don't need to write it as a decimal. That improper fraction is just fine. That's the way we would leave it. This time you see we got a negative result. The first example, we got a positive result. Okay, well, let's continue looking at some more examples. Okay, example 3, evaluate the integral from -1 to +1, x squared times the quantity 2x cubed minus 1 to the 4th power with respect to x. When I say the quantity, what I'm meaning is the following that I'm reading is going to be raised to a power, or in another operation. So the first step, and it's going to be more difficult this time, because the first step is to come up with the indefinite integral. So here we're looking for the integral of x squared times the quantity 2x cubed minus 1 raised to the 4th power. And that's not so simple, is it? But in the, I believe it was the last section, we studied how to use substitution to do integration. And it's not uncommon when we see something in parentheses with a power on it, we think of substitution. That is, we think that we might replace the 2x cubed minus 1 with a u value, because we're hoping to have the integral of u to the 4th here, basically. But to make sure that things go smoothly, what we have to end up doing, remember, is finding what du is. And du is the derivative of 2x cubed minus 1 times the dx. Well, the derivative of 2x cubed is 6x squared, isn't it? And minus the derivative of 1, which should just be 0. So the derivative, du is the derivative times dx. Now, as we go back to our original indefinite integral, this is kind of over here in our notes, isn't it? As we go back to the indefinite integral and we make the substitution, then you see we have a u to the 4th. That's the 2x cubed minus 1 to the 4th. And what we have left over is that x squared and that dx. And we're needing to get a du entered here. So we notice that we're having to replace the x squared dx, so we look for an x squared dx, and there it is. So we need to solve for x squared dx by multiplying on both sides by 1/6. So 1/6 du is actually x squared dx. So that allows us to replace x squared dx with 1/6 du. And then we've seen before that that 1/6 constant can be factored to the outside of the integral. So we'd say 1/6 times the integral of u to the 4th with respect to u. Now that we know how to integrate. So we have our 1/6 that's outside the integration, and we're going to integrate u to the 4th, which says we increase the power by 1, so we get u to the 5th. But we have to multiply that with the reciprocal of the new exponent. And so we end up with a 1/6 times 1/5, of course, which is 1 over 30, and a u to the 5th. But u was 2x cubed minus 1, and of course to the 5th power. Now notice up here, I didn't put plus c because we agreed, since this is going to be used to evaluate a definite integral, that plus c subtracts out anyway. So let's just leave it out from the get-go here. Now remember what we found in this position, this is that capital F of x that we talked about originally. That's what that represents. So now we're ready to do the calculations for the for the definite integral. The integral from -1 to 1 of x squared times 2x cubed minus 1 raised to the power 4 is the function we just, I'm going to put it in big brackets here to emphasize, the function we just calculated, okay, that capital F of x, so it's all of this evaluated from -1 to +1. Remember, from the lower to the higher. Now, something that may not be clear right now. I'll tell you what I'm going to do. I will talk about this after the fact. So what that means we need to do is that first we substitute a +1 into the function. So we put into that function above a +1. That's the top limit, isn't it? So we'll have a 1 over 30. I've got something under my paper here. I'm sorry. Get this organized so that doesn't keep okay. So we have 1 over 30, and we're replacing our x's with 1. So it'll be 2 times 1 cubed minus 1, and that inside is to the 5th power, isn't it? And then we put the subtraction sign for the capital F of -1. So now we're going to take that expression and we're going to replace all the x's with -1. So we have 1 over 30, and then we open our parentheses, and instead of 2 times x, it's 2 times -1, 2 times x cubed is 2 times -1 cubed. And then we have our subtract 1, and then parentheses around that stuff, and a 5th power on those parentheses. So there's a lot of work here. Now, notice, well, let's do some calculations then. So in the first set of parentheses here, we have a 1 over 30, and the inside parentheses have what? Let's see. 1 cubed is 1, 2 times 1 is 2, so we have a 2 minus 1 and a power of 5 on those. And when we come over to this other set of outside parentheses, we have a 1 over 30, and in the inner parentheses, 2 times, well, -1 cubed is -1, so 2 times -1 is a -2, and then we have the subtract 1, and those inner parentheses have an exponent of 5 on them. So we just do a little bit at a time here. The outer the first set of outer parentheses, we have a 1 over 30, and now we have what? 2 minus 1, which is 1, so we have a 1 to the 5th power. And actually, those are kind of those inner parentheses, aren't they? Minus, and over here we have 1 over 30, and now we have -2 minus 1, which is -3, and that has a power of 5 on it, doesn't it? Those are the inner parentheses. Now, we're going to continue here, but here's what I want you to notice, because in the future I'll do this differently. I want you to notice that the 1 over 30 that's in a part of this answer to begin with, that 1 over 30 is in both of these parentheses here, isn't it? And so that 1 over 30 appeared both of these times, in both of these parentheses. In the first pair, subtract what's in the second pair. And so because that appears in both of them, at this point we can factor out the 1 over 30, couldn't we? And if we factor out the 1 over 30, what we really have is a 1 to the 5th minus a -3 to the 5th. And what I'm getting at is we could have factored out that 1 over 30 in the very beginning, and we wouldn't have had to write it over and over and over again. We'll see that in another example, I assume. But anyway, as we continue here, 1 to the 5th is 1. minus, now negative 3 to the 5th power. Oh my goodness, what is that? We'll have to figure that out, won't we? So negative 3 to the 5th power means, you probably are getting your calculator out, I bet. It means multiply negative 3 together 5 times. Is that 5 times? Okay. Now let's keep in mind that when we multiply, well, we can do it this way. This negative 3 times this negative 3 is a positive 9. This negative 3 times this negative 3 is a positive 9. And then we have times this negative 3. Of course, 9 times 9 is 81. And now we multiply with a negative 3. And so we get negative 243. Now we should have recognized that we were going to get a negative result, because when we raise a negative number to an odd power, we'll always end up with a negative result. So here's our, inside these brackets, 1 subtract the result we get when we cube negative 3 is negative 243. So we end up with a 1 over 30 times 1 plus 243, which is 244, isn't it? Oops, I'm at the bottom of the page. Let's go ahead and just go now and say that's 244 over 30. And that will reduce. 2 goes into both of those. 2 goes into 244 122 times, and into 30 15 times. And those two don't have a common factor, so this is our final answer. Now, there was a lot of arithmetic here, but the significant challenge was first finding the indefinite integral. Now, what I referred to, okay, in this problem, to come back over here in kind of the margin, if we end up with, when we're doing a definite integral, if we end up with a constant times some function that we're evaluating from A to B, see, what that would end up saying is that we have the constant times f of B minus the constant times capital F of A. And that constant, of course, is a common factor in this case. And so we can factor it out. And if when we look at that, that's nothing more than the original constant times the function f of x evaluated from A to B. And so the point of all of this is, like I said before, we could have factored that constant out at the beginning, and it just would have been easier for us to calculate. Well, let's go to the next page to look at an additional problem.
Yeah.
Well, I've had a little change in heart here. Before we go on to a brand new problem, I want to show you an alternate completion for the problem that we just worked on. And so let me remind you how we started the problem, is that we needed to find an indefinite integral first. And so we made a substitution where u is 2x cubed minus 1. And so we found du is 6x squared dx, and then found that 1/6 du is x squared dx. And so we were able to replace that x squared dx with 1/6 du. And then we, of course, factored out that 1/6, and we were looking at the integral of u to the 4th with respect to u. Okay. Now, we found out that the integral of u to the 4th was, what, 1/5 times u to the 5th? And so, although I don't think I wrote it completely this way, I substituted the u back in, but we could say that this is 1/30th times u to the 5th. Now, here is where the alternate approach I'm talking about is going to take place. Is rather than putting the value of u back in, that is, rather than putting 2x cubed minus 1 back in for u, we're going to start from here. And we're going to say, okay, look, the definite integral from -1 to 1 of x squared times 2x cubed minus 1 with to the 4th power with respect to x is 1 over 30 times u to the 5th evaluated from -1 to 1. But here's the big deal. That -1 and that +1 represent x values. That's x equal negative 1 to x equal positive 1. And of course, we have u to the 5th power, and so that we can't put a 1 in for x because there's no x, But, okay, remember, okay, this is here over on the side. Remember that u is equal to 2x cubed minus 1. So if x is equal to, for instance, a positive 1, then that means u would be equal to 2 times 1 cubed minus 1, which would be 2 minus 1, or 1. If x is 1, then u is 1. On the other hand, if x is negative 1, then u is 2 times negative 1 cubed minus 1, which ends up being negative 3. So we use this information, and it's called a change of variables. So since we know that when x is negative 1, u is negative 3, we're going to evaluate from u being negative 3 to, instead of x equal 1, u equal 1. That is because of this relationship on the top and this relationship on the bottom. Now we have u values that we can use. So we can put the u value of 1 in first and subtract what we get when we put the negative 3 for the u value second. And then we just saw the results of this. Of course, 1 to the 5th is 1, so this is just 1 over 30. And negative 3 to the 5th power is negative 200, whoops, that's a minus sign, my bad, is negative 243. So we have a negative times a negative, which is a positive, isn't it? We have 1 over 30 plus 243 over 30, which is 244 over 30. And then we simplified that a while ago to 122 over 15. And you see we get exactly the same result. So what we did is we didn't change back. We left it as u's, but we had to change our limits of integration into x values. I think I'll end part 1 here, and then we'll pick up and start looking at some more definite integrals that have a little twist just because they're different kinds of integrations that we do.